Chapter 15, example 2. So this is a interesting problem. The issue here, what we're going to do is add 4 10-bit values and generate a 10-bit output. The problem has some issues as is. So, and these values, they're unsigned binary. So if I add 4 10-bit unsigned binary values, I could, worst case, get a 12-bit number. So this problem specifically says the output's 12 bits also. So normally we'd have to do some checks to see if the internal operations are valid, but this one's a little bit different. So what's going to happen here is we're going to check each of the inputs. If any of those inputs is greater than 255, and remember 255 is associated with 8 bits, if anyone's greater than 255, the whole problem is dead. So what we're going to do is take like a two-prong approach to this thing. We're going to design this as if it's always valid, and then we're going to look for the special cases when any of the inputs are greater than 255. This is actually a lot to this problem, a lot of important things going on in this problem. This would be a good problem to understand. So I'll draw it up here. And they are 10-bit. Once again, this circuit is adding 4 10-bit values. All I have to do for adding is ripple carry adder. It only adds 2 things at a time. So I'm going to need multiple ripple carry adders in this problem. And so what I'm going to do is add 2 of the operands and another 2 of the operands, and then add those results together with a 3rd ripple carry adder. So let's go ahead and draw that. So many ways to do this problem. I'm going to pick the way that makes the most sense to me. There's my rough circuit as is. Certainly if inputs here are 255 or less, the sum is always going to be valid. But for this problem, what I want to do is look at these inputs here and see if they're greater than 255. I'm going to make this output 0. So I'm going to have to adjust this output here. But as is, it works for cases when all the inputs are 255 or less. And the issue here is if I have a 10-bit number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's my 10-bit number. So if all these bits are 1, this number is 255. Now, so the issue is if either of those bits are set, that means this number is greater than 255. So for this problem, later we'll know what a comparator is, but we don't really know what a comparator is right now, so we won't work with it. So the issue is we've got check these 2 bits for each of these 4 operands. If any single one of them is a 1, then the problem is dead. Essentially, not the problem is dead, but the output becomes 0. Let's crank through this thing, and what we're going to do here is use our gate that that looks for a 1. So if at least one of the inputs is a 1, the output's always a 1, and that calls out for an OR gate. Okay, so I'll leave it like that. I think I'm going to have to change that, so no big deal. So what I have here is I've connected these 2-bit buses to these 10-bit bundles, and I need to put a node in this. So that means if any of these bits here are 1, that means this output needs to be a 0. And so when this, essentially if this is a 1, if one of these is a 1, I need this to be a 0. And I have a couple ways to do this. So if any of these are a 1, this output's going to be a 1. But I'm going to take advantage of the notion of an AND gate. When you feed it a 0, it kills the output. When you feed it a 1, it does nothing. So what I need here is not to feed it a 1, but to feed it a 0. And so I'm going to come up here, kind of modify this, and what I'm going to have here is an AND gate. Okay, so this is once again shorthand notation for the fact that this is an AND gate. This is actually 10 AND gates. and they're hooked up like this, where this signal here is connected to all of them, and these are the individual bits of this value right here. Let's just call it sum prime. So this is sum prime. So once again, this is the shorthand notation, and what's going to happen here, if any of these bits are set, this becomes a 1, it gets toggled to 0, 0 on an AND gate, it's going to make all these gates 0, and the output's going to be 0. Whereas if all these inputs are 0, that indicates all those 4 A, B, C, and D's are less, or 255 or less. This is going to be a 0, it gets toggled to a 1, 1 fed to an AND gate allows the other input to pass through it unchanged. And so this is our cheap way of making a decision in our circuit. Notion in this circuit is what controls this circuit, and this circuit essentially has internal control. Internal control is because there's a choice in the output. It's either going to be the sum or it's going to be all zeros, and what decides whether it's going to be sum or all zeros is the condition of those 4 MSBs of these inputs here. I'm sorry, it's the 8 MSBs. There's 2 MSBs. I'm looking at the top 2 MSBs per input, and I think I'm going to call this one done.